The next three chapters, 7, 8, and 9, deal with inferential statistics. That is, where we're using samples to make predictions about a population. As we had discussed in previous chapters, for methods of statistical inference to be really valid, we need to be very careful about how we find the individuals that participate in the survey or an appropriate design of an experiment. So in other words, if data is carelessly or inappropriately collected, any statistical inferences performed on the data is subject to scrutiny. So you want to be very much aware of things like volunteer response surveys or results of internet surveys. So don't give them too much credibility. So what we will do here is the first major topic of inferential statistics is to use sample data to estimate the value of a population parameter. And there are many of them, like a proportion or mean or standard deviation or variance. So we'll go through that. So the population proportion is a percent of population with certain characteristics. And the population mean would then be the population average for a certain measurement. We will also discuss the reliability, the confidence of those estimates, and we will also present methods to determine the sample sizes necessary to estimate those parameters. The first population parameter would be the population proportion. And so let's define a term here called a point estimate, and that's a word that will come up repeatedly. And so the definition of a point estimate, it is a single value or point, therefore the word point estimate, that is used as an approximation, used to approximate a population parameter. For example, what information from a sample would be used to estimate the percent of the population that has a particular characteristic? So first of all, we need notation to distinguish between a population proportion, P, and the proportion that we found within a sample. So here we use P as a population proportion, and that is very often expressed in a percentage or a fraction. And then we have the sample proportion, And so the sample proportion we describe like this, we read as P hat. It's got a little hat on it, so it's easy to remember. So P hat is equal to x divided by n, where x is a number that has the counted characteristics, the number that have the counted characteristic And it sounds a bit abstract right now, but when we look at examples, then you'll see it. And n would be the total sample size, or total in the sample. And we have used that notation before. N is the sample size. So as an example, let's consider a bowl of colored balls your instructor has brought to class. And what percent of the colored balls are red? So we use one sampling paddle to collect at least one sample from the population. So let's say that we take a sample and we count how many balls in the sample. Let's say there are 15. And then we count how many red balls there are in the sample. And let's say there are, 3 red balls. Then the sample proportion would be 3 divided by 15. And that, of course, is equal to 0.2. So we would say that my sample would predict that approximately 20%, 0.2 would be 20%, of the balls in the bowl are red. In other words, by looking at a sample, we're inferring to the total population of all the balls that are in an urn, in a bowl. And so we estimate that from a sample. Now imagine taking more and more samples, maybe of different sizes. And so what we'll find as we look at the shape of the distribution of the samples, we find that the distribution of the sample proportion becomes normally becomes normally distributed. Normally distributed. As we take many, many samples, maybe hundreds or thousands of samples, so the sample proportions become normally distributed, and it is centered at P. It is centered at P. And what was P? P was the population proportion. The population proportion. So it's very important to distinguish between P and P hat. In summary, then, what we can say is that the distribution of sample proportions will be normally distributed. Normally distributed. And the mean of the sample proportion is centered at the population proportion, at the population proportion. And last, the standard deviation of the sample proportion is, it's a little different here. So the standard deviation of the sample proportion. So we have a subscript P hat with a sigma. So sigma, the standard deviation, sub P hat, equals the square root of P times Q divided by N. So we have not talked about what Q is, but Q is simply 1 minus P. And of course, N is the sample size. So we can say, since the sample proportion targets the value of the true population proportion, the sample proportion P hat, the sample proportion P hat the p hat, is the best point estimate of the population proportion, p. Let's look at an example. And that is the percent of households with smart TV sets. In a survey of 1,230 households across the US, 172 households had a smart TV. That is one that's connected to the internet. And the survey included 37 households that had more than one smart TV set. So what is the point estimate here? Well, it is a sample proportion of the households with smart TVs. That is a sample proportion. So in other words, 172 had a smart TV out of a total of 1,230 households. So that makes it 0.1398, or approximately 14% of the households have smart TVs. That is the population proportion. That is our point estimate. So that's p hat equals this. So that's our point estimate of the population proportion, 14%. So in a sentence, if we write it out, we can say that based on the data, the best point estimate, the best point estimate of the population proportion of households with smart TVs, of households with smart TVs is 14%. So that would be a complete answer. In the problem statement, or an example statement up here, we are also told that there are 37 households that had more than one smart TV. So if we want to know the best point estimate for the number of, or the percentage of households that have more than one TV set, then we use a point estimate. And so our point estimate p hat is equal to now only 37 households with more than one smart TV out of a total of 1,230, and that's about 1. So that's about 3%. 3% of households have more than one smart TV. So in a sentence, we can say the best single point estimate of the population proportion of households with more than one smart TV is about 3%. So let's introduce the definition here of an interval estimate, also called the confidence interval. It is a range of values, used to estimate a population parameter. So let me show you in a little graph what that looks like. So here's our point estimate, and from the previous example it was 0.1398, 0.1398, and then we have the so-called margin of error, and we'll talk about that in just a moment here. But let's say there's a margin of error. So this point here would be 0.1398 plus the margin of error, and here it is 0.1398 minus the margin of error. So confidence intervals are of the form point estimate plus or minus a so-called margin of error, which we have not defined yet or explained yet, but we'll get to that in just a moment. So this is the margin of error. Here's the point estimate, and then plus the margin of error minus the margin of error. And the margin of error is really based on three things. It's based on the standard deviation of the sampling distribution. So the standard deviation of the sampling distribution. Is based on the sample size, n, and it is based on the confidence level, confidence level we choose, the confidence level we choose. So let's talk about the confidence level, because that is a very, very important concept here for this chapter and the future chapters. But the confidence level is the probability, that the confidence interval captures the true value of the population parameter. So here we are assuming that the process is repeated a large number of times. And the most common choices for the level of confidence are the 90% confidence level, or CL, abbreviated quite often, the 95% confidence level, and the 99% confidence level. Now, interpreting a confidence interval, we must be very careful to interpret confidence interval correctly. For example, let's say the 95% confidence interval is for P, for population parameters between 0.924 and 0.858. When we are saying we are 95% confident that this means we are 95% confident that the interval from 85.8% to 92.4% actually contain the true value of the population proportion P. So again, we are 95% confident that the interval from 85.8% to 92.4% actually contains the true value of the population proportion P. Let's talk about the level of confidence. The level of confidence is the proportion of intervals created by this method that would be expected to capture the target parameter. In other words, here's the population proportion, if a large number of repeated samples are obtained. So let's go over it one more time. The level of confidence is a proportion of intervals created by this method that would be expected to capture the target parameter if a large number of repeated samples are obtained. For example, a 95% level of confidence means when computing confidence intervals based on different samples, 95% of the intervals will capture the true value of the target parameter. In other words, only 5% of confidence intervals created with this process will miss. So here we have confidence interval. Here's the target parameter. And so here's an example where this confidence interval captures it, this confidence interval captures it, but this interval does not capture it, but the others do capture it. So 95 out of 100 would capture the true target parameter. So, in this correct interpretation, the level of 95% refers to the success rate of the process being used to estimate the proportion. And you may go over these definitions a few times before it really becomes part of your thinking. It is a different kind of a concept for most people. So if it doesn't sink in right away, I understand that. But I would just suggest to go over the definitions a few more times and reread them, maybe read them out loud, and then you will get the meaning of it. The next important concept is that of critical values. And the confidence level is used to find critical values. As the words indicate, they must be important, and they are. So critical values. And critical values are symmetric z-scores that create a probability area in the middle of the standard normal curve equal to the confidence level. And so in other words, alpha is the complement of the confidence level. Alpha is the complement of the confidence level. For example, if the confidence level is 95%, then alpha would be 5%, because then 95% plus 5% would be 100% or 1. So if that's the confidence level, then alpha would be equal to 5%, or 0.05. So alpha is the area outside of the confidence interval. So alpha is the area outside of the confidence interval. Confidence interval. So alpha is equal to 1 minus the confidence level. Confidence level. And then alpha divided by 2 is simply the area in each tail. Area in each tail. And so the critical values are denoted by z sub alpha divided by, or minus z sub alpha divided by 2, and z sub alpha divided by 2. So graphically, we have the confidence level here in the middle. Let's say it was 95%. That means we have 5% as the total area of alpha. Then alpha divided by 2 would be 2.5% in each tail. So, for example, for a 90% confidence interval, there is 5% in each tail. 5 plus 5 would be 10%, so 90 plus 10% is 100%, or 1. So the critical value for 90% confidence levels is z sub alpha divided by 2, and so it'd be z sub alpha 0.05, z sub 0.05. And what does that mean? Well, that means that the area here has to be 5%, or 0.05, and whether we use technology or simply look up in the tables what that value is, it is 1.645 on the positive side, and since it's symmetric, minus z sub 0.05 would be minus 1.645. So that would be the area on this side. Of course, it would also be 5%. So we're asking ourselves what value that z has to be greater than or equal to, would that area be 0.05? And again, whether we use technology or look it up in the tables, it's 1.645. The probability that z is greater than 1.645 is 0.05, the area under the curve here, the little tail. Similarly, for the 95% confidence level, since there must be 5% combined for both tails, there needs to be 2.5%, 2.5%, or 0.025 in each tail. So again, we ask ourselves, what is the probability for z greater than or equal to question mark equals to 0.025? And again, whether we use technology or use the tables, so we find that value is 1.96. So the probability that z is greater than 1.96 gives us an area or probability of 0.025 or 2.5%. So we can say that z sub 0.025 is equal to 1.96, and then again symmetrically minus z sub 0.025 is equal to minus 1.96. So for the 99% confidence level, that means we want 99% in the middle, 99% or 0.99 in the middle. That means that the two tails together have 1%, or in each tail there's 1/2 of 1%. So it's 0.005 would be the area in each tail, or the probability 0.005. So together, of course, is equal to 1. So we have 99% or 0.99 in the middle, and then 0.005 in each tail. So we're again asking the question, what is the probability that z is greater than question mark? So that area is equal to 0.005. Again, whether we use technology or we look it up in the table, z greater than or equal to 2.576 standard deviations above the mean. That would give us an area of 0.005. So we can say the critical value for the 99% level, so there's 0.01 in each tail, no, 0.00, sorry about it, in each tail is 0.005. So we can say the critical value for z sub 0.005 is equal to 2.576, and then the negatives, the opposite would be minus the 0.005 would be minus 2.576. So these are the critical values for the 99% confidence level. So we can summarize everything very neatly here, and we can just put it in a little table here, and we say for the confidence level of 90%, alpha divided by 2 is 0.05, and the critical value, z sub alpha divided by 2, would be 1.645. For the 95% confidence level, the alpha sub 2, alpha divided by 2 would be 0.025, and the critical values are 1.96. And for the 99% confidence level, alpha divided by 2 would be 0.005, and the critical values would be 2.576. It's good to have this little table available when you do confidence level, margin of errors. That's really what it's about. So here's what it means graphically. This would be our confidence level. Confidence level. And then the area in each tail would be alpha divided by 2. Alpha divided by 2. Alpha. And then z sub alpha divided by 2 would be this point here. And minus z sub alpha divided by 2 would be this point here. Now we're in a position to finally define the margin of error numerically, so to speak. And that is the margin of error, E, equals z sub alpha divided by 2 times the square root of p hat q hat divided by n, where p hat is the sample proportion, and q hat would be 1 minus p hat, and n is the sample size. Sample size. Now remember what this quantity really is. That is the standard deviation, for the sample proportion. And we had defined that a few minutes ago. So that is the very, very important margin of error. And again, this is multiplication. Z sub alpha divided by 2 times the square root of p hat q hat divided by n. And let's apply our newfound knowledge about the margin of error to the previous example of the households with smart TVs. So here it is computing a confidence interval. In a survey of 1,230 households across the US, 172 of the households had a smart TV. Using a 95% level of confidence, find E, the margin of error for the proportion of TV households with smart TVs. Okay, so for the 95% confidence level, we know that Z sub alpha divided by 2 is equal to 1.96. Look at the previous table of values that we had here just a moment ago. And we found out that the point estimate, p hat, was equal to 0.1398. That would give us q hat 1 minus 0.1398. So q hat would be equal to 0.8602. And of course, n is equal to 1,230. So we can compute our margin of error as E equals Z sub alpha divided by 2 times the square root of p hat q hat divided by n. So there would be 1.96 times the square root of 0.1398 times 0.8602, all divided by 1,230. That's supposed to be an n here. And when you calculate this correctly, this comes out to 0.194. So then that's our margin of error. So we can say that's plus or minus 1.9%, roughly speaking. So then the 95% confidence interval is a point estimate plus or minus the margin of error. So p hat plus or minus the margin of error. So that means it is p hat plus or minus E, which in this case is 0.1398 plus or minus 0.0194. 0.0194. So that means the true population parameter is between the following values. So in other words, 0.1204 is 0.1398 minus 0.0194, that's 0.1204, and the right boundary for the margin of error would be, or for the population parameter would be 0.1592, which is 0.1398 plus 0.0194. In summary, we can say with 95% confidence, this data predicts that the true population proportion of U.S. households, with smart TVs, is between 12% and 15.9%. And that includes a margin of error of 1.9%. And the overall goal is to have a high confidence level, is to have high confidence level in our prediction. And while still providing as narrow prediction interval as possible. While still providing as narrow the prediction interval as possible. Because a narrow prediction interval gives a more precise estimate.